Hi everyone, I'm Gangamini Pratibha. Welcome to my YouTube channel again. Today I'm going to cover up from this video PRIM's algorithm is a minimum spanning tree. PRIM's algorithm, a fundamental concept in graph theory. Today I will break it down step by step to make it easy to understand. Let's begin. PRIM's algorithm is an efficient method to find the minimum spanning tree of a weighted graph. It starts with a single node and continuously adds the smallest possible edge that connects to a new node. Let's see what are the key concepts of the PRIM algorithm. Here are three concepts of the PRIM algorithm. Before diving into the algorithm, let's understand some basic concepts. The graph consists of nodes and edges. If these edges have weights, we call it a weighted graph. The minimum spanning tree is a subset of the graph that connects all nodes using the minimum total weight without forming any cycles. Now, let's go through the steps of PRIM's algorithm. We start with an arbitrary node. Then we find and add the smallest edge connecting to a new node. We repeat this process until all nodes are included in our spanning tree. Here is an example graph. We will use this to demonstrate how PRIM's algorithm works. Each edge has a weight. This is the weight in between D to D vertex. This weight is 8. And our goal is to connect all nodes with the minimum total weight. Here is a new example. Now let's go through the algorithm step by step using our example graph. We start with a node, then choose the smallest edge that connects to a new node. We repeat this until all nodes are connected. In PRIM's algorithm, we should have to remove self-loops. What are the self-loops in this graph? Let's see. 1. Here, B. B has a self-loop. It has a weight. The weight is 1. And B has also 2 loops. Here, those loops have weight 2 and here 2 and 9. And you also have self-loop 4. And we should have to, before I told you, first we have to remove self-loops and parallel edges from the graph like this. Okay. Then now let's remove self-loops. In this graph, you can see after remove self-loops, we had self-loop and we had 2 self-loops and we also have a self-loop. Now all self-loops are removed. Okay. After remove the self edges, select any node as the root if the root is not given. Let's select A as the root and mark adjacent edges as taken. Let's see how we can draw this after remove self edges and after select A as the root. This is after the remove self edges. We should have to remove those self edges with their weights. In this case, I got A as the root. I told you, if the root is not given, we can take as our choice a root. A, B. In this case, we can see A, B, C, E, D, F. There are many roots, and I got the root is A. Okay, after select the A as the root, the connected edges we can see A to C and A to B. A to B and the A to C. Then I told you all edges have weight. A to C weight is 3. A to B weight is 5. In second step, I told you we should have to get, in this case, minimum weight. Minimum weight with the edge. In A to C and A to B, we can see the minimum edge. A to C is 3, weight is 3, and A to B, weight is 5. The minimum weight is A to C is 3. Then we can take the C and put the weight. Then we should have to get A to B, because it is the next weight we should have to get. In this also A to B weight also we should have to put here like this. And then after that, take those weights with edges. We should have to mark. Then we can name it taken. A to C taken. It is here. And the A to B weight is also here. It is taken. After take those weights with edges, we can name it as taken. Then next, here are some. Next minimum value, we can see the 6. Can we take the 6 C to B? No, actually we don't get C to B edge because of, in this PRIM's algorithm, we cannot build cycles. If we make cycle in PRIM's algorithm, it's wrong. Okay. Then next, we can check next minimum values. C to E, we don't take C to B, because if we get C to B, it can make a cycle A, C, B, A, B, C. Okay. Then next minimum value we can get C, E, edge, and B, D, edge 8, C, E 7, and B to E 12. We can take C to E. It is the next minimum value. Now we select C to A edge. Then we can say it's a taken edge. like mark adjacent as taken, and we should have to put the weight, and next node is E. Okay. Then B to D. No, we cannot take it because it is a high weight. After come to the node E, it has several edges. We can take the minimum value edge to D, or it has, I tell you now, E has several edges, E to C, E to B, E to D, and E to F. Here, E to F. Let's take E to F. Before we mark, before we take E to F edge, we should have to mark as taken. Don't forget to put the weight. The next minimum value is E to D. Okay. And next we have to put the weight. E to B. We cannot take it because if we take the E to B edge, it make cycle. It is the reason we don't take E to B edge. Okay. This is the after remove self edges. This is this example, and this the minimum with minimum value PRIM's algorithm. This is after we sorted the spanning tree. This means minimum spanning tree. After sort the spanning tree. In our pre-slide, I tell you how to take edges and how to choose minimum weight edges and how to draw these step by step. I hope you can understand this how to draw this minimum spanning tree. Here, this is the final output. Here are the step by step how to draw the minimum spanning tree. Here is the algorithm with edges and with self loops. First, we should have to remove those self loops with weights. This is after remove self loops with their weights, and after we sorted those edges and the output. Here you should have to put their weights. You must put their weight while you are drawing this minimum spanning tree. This is a summary of drawing minimum spanning tree. Okay, From our pre-slides, I told you how to draw a minimum spanning tree stepwise. Here, PRIM's algorithm has many applications. It used in designing network infrastructures, circuit layouts, and even road and railway networks to minimize costs while ensuring connectivity. Here is the conclusion of PRIM's algorithm, minimum spanning tree. To summarize, PRIM's algorithm is an efficient and powerful method to find the minimum spanning tree. It ensures minimal cost, connectivity, and is widely used in real-world applications. Okay, thank you for joining with DSA Academy. Let's meet with the next lesson.